Okay, hello everyone and welcome back. This is our last session for the day. For those of you who've been here from the beginning, thank you so much. This is going to be a session on ultrasonic testing methods, and we're going to be particularly looking at the ways that we can detect different defects and voids with these tools, and covering ultrasonic pulse velocity, ultrasonic pulse echo, and impact echo testing, which I sort of consider to be three tools with a lot of crossover in how they get used. Just 1 second. If you just escape, that should let you. Awesome. So again, we're recording these sessions, and I'll try and leave some time for questions at the end. I will put a hard cap on 5 o'clock for the day, but I'm hoping to be finished by 4:30. All right, for those who haven't seen me earlier, I'm William Ward. I'm the New South Wales manager at PCTE. So this is the final session I'll be covering today. Still on the board is Joel, and he's operating our equipment and making sure you can see me and see our presentations. Let's do a little bit of physics. So if we want to measure sound waves, we need to establish what sound waves are. We also need to bring in a bit of an understanding that not everything that the manufacturers call sound or ultrasound is actually what we'd think of as sound. They just use it as a shorthand to describe sonic and seismic testing. So I'm not giving you a full overview of how different forms of stress and strain energy are carried through solid materials, liquid materials, and gaseous materials. I don't have that capacity. But I'm going to talk about a couple of different forms of energy that we commonly measure in some of the different machines that I consider under ultrasonic testing, or more correctly, seismic testing. The first is what you're hearing right now. It's compression wave energy. This is sound. Sound can be carried through air, can be carried through water, can be carried through solid materials, and it is a compression and expansion in the direction of the source. Now, if we have a side-to-side motion of a source, we'll term that shear wave energy, which has different carriage properties and is quite commonly another form of energy we hear referred to as ultrasonic. Particularly the ultrasonic pulse echo devices that you will mostly see are actually ultrasonic pulse, they're shear wave arrays rather than sound arrays. It has a couple of property differences, the main one being in the speed of transmission. So let's hit something. Hitting something is a good start. It's been a long day, time to do some damage. If we strike homogeneous material, we're going to form fronts of different forms of wave energy. The fastest energy is going to be our sound wave, or our compression wave energy. P wave is another way to refer to this. I've got that in orange in the outermost arc on my screen. Then we'll have the shear wave energy from that strike, which is going to be a bit slower, about 0.62, 62% as fast. And that's the green wave. And then there's a third form of energy. I'm not going to go into a lot of detail, but does get involved in some of our more specific specialized seismic tools that go beyond the scope of this presentation, and that's Rayleigh wave or surface wave energy, which is confined to the surface or to a particular depth, and we use for some interesting properties in more advanced testing. But compression wave's fastest, shear wave's slower, and this is something we can take advantage of. So the first thing is, if we put a sensor some distance from our strike or a source, we can pick up the speed of the compression waves very easily. We know when it goes, and then we can listen for when it arrives, and then we can just work out that time. So we don't have to muck about trying to isolate which energy source it was. If it got there first, it's sound, it's compression wave, it's P wave energy. Easy. It's also omnidirectional. Now this sources we've got, compression wave sources, or just giving it a whack, they're omnidirectional. So if we give a strike in the middle, energy is spreading out in all directions. Now the reason shear waves are quite commonly used is we can tweak our configuration. We can produce what's called a dry point contact transducer to induce only shear wave energy in one orientation. So I've got that orientation mocked out on the screen. The red dot moving up and down is a big exaggeration of what a point contact shear wave transducer is doing. So it's introducing shear waves perpendicular to its side-to-side motion and compression and Rayleigh waves parallel to its direction of motion. Once again, we've got a clean output. If we look at a line perpendicular to the side-to-side motion of our shear waves, we know that the only energy along that path is going to be shear wave energy. That's very convenient because we can use that to, rather than having to do a 3D problem, we can do a 2D problem, just like with a radar scan. We can take a slice along that line, put some other sensors along that line, and we can produce an image. That's what the ultrasonic pulse echo techniques do, and that's why most ultrasonic arrays are actually shear wave arrays, because of this ability to isolate along a particular slice path. So, ultrasonic pulse velocity. This is going to be the first technique I'd give you a little bit of theory on, because everything else we do starts with the kind of hardware and the kind of measurement we do with ultrasonic pulse velocity. This is the Pundit from Screening Eagle or ProSec, and it's just been doing very simple compression wave pulse velocity. So we can see that it's a point-to-point transmission. We send from one transducer, it passes through a material, and we receive it at the other end. Our raw measurement is in microseconds, but we usually give it a piece of geometric information. We're going to give it our distance between the two sensors. You can maybe bring the slides a bit bigger, they'll be tricky for some people to see. Yep, so if we give it, in this case, that 250 millimeter distance, we can then take that we take that time of transmission and we can calculate velocity or speed. So ultrasonic pulse velocity, that's the default measurement. With newer machines, rather than just waiting for the first arrival to trigger a sensor, we do now record the waveform. But something I will warn you about pulse velocity interpretation, even though you have access to the waveform, just visually looking at the shape of the waveform isn't going to give you a lot of information. The shape of that waveform is primarily controlled by the nature of transducer you've used, whether it's a lower frequency 24 kilohertz or 54 kilohertz transducer, or it's a higher frequency transducer. Your material it's being transmitted through isn't going to make a large change to what the human eye can see. Now, if you're a researcher, you can do all sorts of interesting signal processing outputs and that, get lots of sensors and do all sorts of clever things. But for people working on site, I encourage you to limit yourself to 2 points of interpretation, which is the time of transmission, so your velocity measurement direct, and maybe a little bit of amplitude analysis, which is how strong was the received signal. But please don't go thinking you can see shapes in the actual waveform receipt itself, unless you'd like to know who you're going to marry next week. So for devices we have available, it's the Pundit range from ProSec. The Pundit PL200 is the latest device. It's a particularly good device for field testing. If you're running a small lab, there's also the lab device available, works with the Windows computer, just a different option where appropriate. Now, the big trick to understand is that whenever we're using signal collection tools, and this is even true of radar, we just don't go into the details so much, the only bit we actually care about is the time where the sound goes and is received. But the device itself has internal circuits. It has to transmit that energy through cables, which is speed of light effectively. So the reason that you'll see those calibration bars with your pulse velocity devices is they're used to eliminate any time lag from the measurement in between the sender and receiver. And also we need particular electronics to produce pulses that'll trigger the test and give us all that information. In terms of what we expect to find, if we're talking concrete, well, concrete is not a homogeneous material. If you'd give me steel and the type of steel, I can tell you the number it should be. This is why we do so many clever, very elaborate work with steel ultrasonics, but with concrete, it's rock, it's sand, it's cement, it's water, it's admixtures, it's all inhomogeneous, it scatters the signal dreadfully, so we've got to use big clunky transducers. It's not a very friendly material, and it's not a predictable material. So rather than knowing the number it should be, the speed of transmission, we're going to give it somewhere between 3,000 and 5,000 meters per second in typical concretes. Let's talk about transmission. If we know the path of the signal, either directly from one side to the other, or maybe we can go around a corner and do a semi-direct measurement, that's going to be the best case for setting up your pulse velocity measurements. Because with a controlled signal path, we have a controlled distance, and we know how it's going to behave. Everyone asks me, well, what if I don't have access to both sides? What if I put the sensors on each side? We do not know the path of an indirect transmission. So if you see in my little example here, it may be directly through the cover concrete, it may go some distance through the surface. It's not a predictable measurement, so an indirect, and it definitely doesn't bounce down and echo back like you might do with some metal ultrasound or some other tools. So practically, indirect measurements are always going to appear slower than the same distance measured direct or semi-direct, and should not be compared. We do have some devices for indirect measurement. They work quite well for characterizing different materials. You know, if this one's faster, this one's slower, that's meaningful. But if you want to do something like find voids or evaluate the internal element of concrete, we've got to have access for both sides to use a ultrasonic pulse velocity device to do that job. And again, quality, faster the better essentially. And defect detection, it gets slower. So if we know the speed through unvoided, undamaged, correct concrete, we can look for regions where it slows down. And the slowing down could be quite subtle. It might be 10% or so if we're getting a reliable test that it slows down to a voided region with limited voiding. So that's pulse velocity. I'll have a lot of examples of how it looks with different problems in the second half of the presentation, but that's the theory behind it. The next one is ultrasonic pulse echo. So I've already told you we can't do echo measurements with pulse velocity devices. We can do it with our shear wave ultrasonic pulse echo devices, and we'll be able to take the value normally as a thickness, because most of the pulse echo devices have either the ability to ground truth and set the depth like we would with a radar, or to take a measurement of the speed of transmission of those shear waves through the material to give a rough depth. So we normally view pulse velocity data as depth. Particularly sensitive to voiding for two reasons. One is if you've got a big enough void, it'll bounce it back or scatter it. And if we've got small voiding, it can slow it down and affect it. So all of our sonic devices are what we're going to be using for our void detection work. But the big reason people use pulse echo in favor of impact echo or ultrasonic pulse velocity tests tends to be the visualization. So the visualization, are we coming in clear, Joel? Tends to be the visualization. So the PD8050 is Screening Eagle ProSex ultrasonic pulse echo array, and it's an array. That means we're taking multiple measurements with each data point of collection. And we also have, for further post-processing, the Pundit Vision software, which is a useful tool for when you've got more detailed data analysis. Again, a little beyond the scope of today, but I want to highlight we've got a tool for more advanced or research work as appropriate. The dry point contact transducers don't need any coupling. So with the UPV transducers, you saw the big blocky metallic ones, got to use gel, we've got to get the sound in. With this tool, well, we've got little ceramic dots, they move, they put the energy in, they collect the energy. But the big differentiation on this device is the multi-channel array. So we've got 8 points of contact. Each set of 3 transducers acts as a single point of measurement or point of transmission. And we have about a roughly 50 kilohertz frequency on it. And what it does is we'll send from one and we'll receive on the others, so we can do a visualization of the region underneath that transducer. Now, first thing to notice with this particular measurement, there's more detail in the middle than at the edges, so we tend to overlap our measurements if we're stitching them together. So that's 100 milliseconds, about 28 measurements, which we make into our visualizations you see with the device. I'll show you some ultrasonic pulse echo data in a second too. Now, the final test technique, one of my favorite test techniques, is impact echo testing. I do have a full webinar on this technique. I don't know if it's on YouTube yet. I will put it up. I'm also game with anyone who's looking at impact echo equipment to help them get their trial done successfully and teach them to use this technique properly. The big difference with impact echo compared to your pulse velocity and pulse echo techniques is we've gone from a transmission and receipt based technique to a test of resonant frequency. So we're still using compression waves as the energy source. We're striking the surface. But rather than record, when does my signal come back, we're recording effectively the sound inside the concrete. We can convert this sound data to a dominant frequency by doing a bit of signal analysis. What we do is we convert from frequency, we convert from the time domain to the frequency domain. We look at the distribution of the frequency in the test, and that gives us 2 bits of information. It'll tell us the thickness, if it's solid and plates and potentially flat and simple. And if it's a little more complicated, we've got a repeating test we can do that will change in regions of problem. So in terms of equipment, we've got the ProSec PI8000, which is a combined impact echo and pile integrity testing device. Excellent value, excellent tool where you've either got pile testing to do with a lot of clear documentation or you want a multi-purpose device for your business. Our more advanced impact echo testing options come from Ultrasonic Instruments, and they allow more control, a lot more variation of impacts and frequencies and setups to do more complex work than you might do with a simpler device. Now, this is basically the classic diagram of impact echo, and it's wrong. All diagrams, when you look at a diagram, they're about 80% true, because unless I can show you a simulation of what it's doing and have you understand all the physics and mathematics behind that simulation, I can't visually show you how this test works. But this gives a mental model, just like with our cover meter, box sensitive to metal. Impact echo, give it a whack, see what sound comes out, convert that sound. The one thing I've got a particular problem with on this technique is the left-hand representation, where it shows the sound going down and echoing back. I consider that to not be true, because what we're actually measuring is the overall response, the repeated echoes, the dominant repeating energy from that strike. And our practical output is a chart that shows the frequency from that strike. So that's the one thing I argue with on that particular drawing, is the output is a repeating signal, essentially a conglomeration of sound energy. We can extract frequency and thickness from that. It's not an echo as such. The name is misleading. It's a resonance test. Impact echo does have a few special constraints. So all of these techniques, you do need to be able to get your sensor onto uncoated concrete. It's sound. I can't listen through a carpet. I can't listen through paint. Once I've done that, with impact echo, because it's resonance based, I have to be mindful of my geometry as well. I can't get too thin. The limit's probably about 50 millimeters with special devices. With regular devices, about 100 millimeters or more is more appropriate. If you're going very thin, you need to let us know and help us specify out the right tool for the job. Can't have any surface coatings. We also need to look at keeping away from circular sections, corners and edges, and joint details, because they're going to take what should be a simple resonance test of a flat or simple geometry to a complex response. That's going to be very hard to interpret and work with. The other thing worth being aware of, and this is also true of ultrasonic pulse echo, if we've got a break, like a delamination or a cold joint, that is, with the sensitivity of these techniques to damage or air gaps, even a slight crack along the face perpendicular to where we're testing, it'll stop the signal. So you'll either measure the thickness down to that delamination, or the test will be too thin and it'll go a bit crazy. We can't see past the first defect. And that's like with the radar, we can't see past the first metal. With ultrasonic, sensitive to air, can't see past the first air. So, back to our final talking about what the goal of the job is. We've done this each time, except a little bit during corrosion, because that was Ruben's presentation. What do we want to know? Do we want to compare quality, like with the Schmidt hammer? Do we want to get an idea of this concrete's the same as this, or this concrete's different to this? We can do that. If we can get a nice, clean bit of homogeneous concrete, do a pulse velocity test or one of these other tests, the result will change if there's some qualitative difference between it, maybe a different strength, or maybe if we've got some minor voiding or honeycombing, if the consolidation is bad. These techniques, especially impact echo, and to a lesser extent pulse echo, and UPV is quite good too, if it's through the honeycombed region, we can look for that poor consolidation. Now, big blobs of air, yes, absolutely, all day, no problem. Embedded objects, I don't like it, but there's sometimes you have to use it. Examples are some of the pulse echo arrays have been used to locate rebar depth and position, but only where it's steel fibre reinforced concrete. If you could use a radar or a cover meter, why are you mucking around with your sound waves and complex tools with poor sensitivity? But if you can't get anything, something's better than nothing. Now, delamination, great for detection. Strength, there is a strength relationship on pulse velocity, just like with the Schmidt hammer. I mentioned that a bit during the Schmidt hammer presentation. We've also got some slightly loose relationships to crack depths and some pretty good tools for thickness measurement. Once again, we've got to define which machine are we going to use, how are we going to use it on site, do we actually have the access to get a sensor onto the surface, facing the problem we have. One of the big questions we get is, well, what can I do about vertical cracking? And the answer is not a lot, because I mean, what are you going to bounce off it? It's usually just in line. What sort of data logging function? You'll find with all of these tools, you're probably going to be setting up grids or setting up some way to take more than a single measurement, because it's pretty meaningless by itself. You want to compare a larger data set, so be mindful of grid setups and learning the data logging of your devices, because all of them, they look simple to use, but you'll find if you haven't practiced before you go out on site, you'll make mistakes, you'll need to redo the work 2 or 3 times. A bit of practice ahead helps, and just be aware, what do you want to show the client at the end? So the final portion of this presentation, I'm going to show some different problems and just point out which devices are going to be appropriate in each case. The first case, thickness measurement. What can we do for thickness? Well, we can't use pulse velocity, it doesn't work from one side, but all of our other techniques are impact echo. If we are away from the edges, great for thickness on homogeneous. Ultrasonic pulse echo, it's practically in the name. It's going to give us thickness, no trouble. And also, if we actually can get radar and the depth penetration of radar is suitable, we can often take thickness off with radar as well. The limit with radar is depth, because radar probably 500 to 600, 700, absolute maximum. You'll find that the thickness depths for your ultrasonics might go further, maybe as much as 1 meter or a bit more. There's specialized arrays being used on dam walls of many, many meters, but a bit outside the scope of what we're doing. And how do we present it? Well, with impact echo, we're not going to show a single test. We're not going to confuse people with frequency graphs and complex interpretation. We're going to give them what they want. We're going to give them a grid map of thickness. This blue map was taken on a boat ramp, the slab next to it, so it got thicker as the boat ramp went down. So we just graph it out in a grid, thin on the left, thick on the right, increase in color. Something I'll point out about this color. This was a graph of thickness. It wasn't a graph of defects. What color did I leave out? I want answers from the room or from the chat.
Red.
Yes, that's exactly right. If you put red in your visualizations, or if you go away from bipolar color schemes or intensity-based color schemes to schemes with multiple colors, your clients or someone 20 years from now who hasn't looked at that report is going to make their own conclusions on what that color means. And if it's red, well, either they're going to get angry because they're a bull at heart, or they're going to think it's bad. So be mindful when you're presenting information, everything speaks to the language. so a neutral color like blue, and an intensity scale, bipolar, white to black, white to blue, something like that, will often be a clearer tool when you're not trying to show here's good, here's bad, but you're just trying to give someone information. Same with radar. This is why we don't like to use the spectrum view on bipolar data for radar, because then the user starts to interpret all sorts of crazy things in there. Same thing, pulse echo this time. So we do have thickness on a grid as one option. But I know I've got some red in this. That's because I'm presenting intensity data. One of the areas we tend to step back from this a bit, and you see this with our migrated view, when we want to interpret amplitude as well as position, we might use a blue to red just to show that the red is a louder sound, or in this case, a stronger shear wave reflection. And that makes sense, it's closer to the surface. So the pulse echo results, the lower blue chart is a slice, like a radar slice through. It's quite heavily processed because the technique pulse echo devices use is a form of synthetic aperture imaging. Essentially, essentially similar to radio telescopes where you don't have one big lens, you've got lots of individual point receivers and a mathematical lens. We do the same thing with the arrays. We make more out of the shot than we'd otherwise have. This is very much in the weeds, but the way we'd use it is PD8050. You'll use this kind of tool to do to do a slightly bigger geometry job, because it'll give you a visual slice like a radar will, greater depth, nice imaging. Pore consolidation or honeycombing. This is one of the big ones. Because this is something which people are like, oh, can I see it with the radar? Can I find this problem? I've just had this bad pore, what do I do? Now, if it's really, really bad, sure. If it's got big blocks of nothing, radar will work. Bondec, not Bondec, I apologize. Some of your plastic formwork systems or your cement fiber formwork systems, if they get really empty, yeah, you can use radar to find voids in there. That's quite commonly done, as is thermal camera work, a bit beyond the scope of my presentation. But with the tools we're talking about, our pulse echo arrays, our impact echo, our pulse velocity, if we can get any of them over top the region we're checking, they're going to be very responsive. So if it's going to be UPV, we'll want to have the signal path directly through the expected honeycomb region. If we move away from the honeycomb region, the signal will return. It's a direct transmission. If we're doing impact echo, we have a frequency shift. Typically, it'll be a little bit more hollow. So we'll go a little bit lower frequency. So we'll see that if we were viewing the data as thickness, it'll look a bit thicker when it voids. So again, that's that small comparison. Again, for full details on impact echo interpretation, data processing and filtering, I've got this in more detail, but just to give you the overview of how we interpret it. All sonic tests are great for delamination, just got to get over top of it so we can't get inside regions where we can't put a sensor. Other than that, any of these are going to work. Something worth highlighting for delamination, and to an extent your honeycombing too, with ultrasonic pulse echo. It's a reflection-based technique. So sometimes if your surface is rough, like a spalled underside or some sort of damage that doesn't give you a flat surface to bounce the signal back to the sensor, we find our result being scattered data. So in this case, illustrated quite nicely, it's a spalling underneath an element, which we detect not by having the element look thinner, but by the reflection of that thickness vanishing. So something with all ultrasonic pulse echo data you ideally want to have is a visible reflection for your thickness, because we can watch that reflection and see if it vanishes for interpretation. We won't be able to do that if we have a very thick element, we can't see the other side of it. It limits the use of UPE in that concept. Same with impact echo. If we don't have a repeating frequency we can measure, we don't have something easy to work with. Now, void formers are basically like a thinner concrete. Big voids are like void formers. So we get thinner on our impact echo test. We simply go to a higher frequency. That means a thinner result. With impact echo, with ultrasonic pulse velocity, we tend to get slower because it's got to go around or through and it gets weaker. And again, got to be directly through the path of that void. And we also have, with the ultrasonic pulse echo now, we get visual detection. We can actually see lumps where they shouldn't be with our arrays. So you asked a bit earlier today about what do you do if you've got voids near to your reinforcing. Maybe this is something that would be sensitive to your impact echo or your ultrasonic pulse echo tools. So now subgrade voiding is a bit different. So with subgrade voiding, we tend to use specialist techniques. Because impact echo won't work because we're testing inside the concrete, not underneath it. So if we want to look for scouring, we might use a technique called slab impulse response. It does what it says on the box. We give it a great big whack and we see how the slab responds. And we just basically we see if we can move it under hammer blow. Or radar techniques, if they're not being used in steel fibre, something that'll stop radar, can show a different reflection from air versus soil. So there's a couple of good tools for subgrade voiding. Slab impulse response sees a lot of use in our tunnelling work in Sydney and elsewhere, where they use it to check for voids beneath the tunnel lining, because that's steel fibre reinforced tunnel panels. They want to put cement grout behind it. They want the grout to be solid. Give it a whack, see if it moves. And that's the kind of results that this data will produce. So radar on the left, red for stronger signal. Intensity of motion, slab impulse response in the middle, red for more motion, and then voids underneath the moving bits. Cracking, well, if it's underneath the test head, we can find it's like a delamination. If there's lots of, like micro cracking, good luck, it really doesn't do a lot to the test. I wish I had a good solution to give you for how bad is the cracking now that we've got a width of 0.3 millimeters and it's beyond our spec. That's a difficult job. It's very hard to do. But we do have a little bit of ability to find cracking in the regions of the test, and we do have a fairly limited crack depth measurement tool, more of a crack depth estimation, by which I mean you've asked about accuracy a lot in the previous thing. This is my way of saying not very accurate. I call things estimates when I really don't want the numbers being used to nail down an answer, a go or no go. They don't have the strength of quality on them. That's my final note, that's my final presentation. Are there any final questions? Anything? Anything on the chat, Joel? All right. Well, this has been PCT's New User Day. I will at some point go through a whole day's video recording and make something out of it for general consumption to share with your colleagues. If you've got any questions that come up further, send me an email. We'll certainly be sending out some advertisements to people who registered to attend about our end of financial year sale coming up in June. And it's been a pleasure to present for you today and to introduce you to some of the rest of PCT's team. Thank you so much.
Thank you.